Hello, class. Here's a brief overview of how free body diagrams are applied to solve a problem. The first step with a force problem is to establish a coordinate system and sketch the force vectors applied on the object. Next step is to sketch each force component in the x and y direction. If appropriate, Newton's equation can therefore be applied in each direction separately. This particular problem has a basic vector problem of solving for the resultant force. This next example here, we want to calculate the sum of two forces exerted on a boat by worker A and B. Step 1 is to draw your force components on your object in the x and y direction. Just like we did with vector algebra, add up all the components in the x and y direction separately. In the x direction we have Fax and positive Fbx. In the y direction, we have positive Fay and negative Fby pointing downward. We don't know the values of Fax or Fbx, but we do know the resultant values and its direction. By applying trigonometry to these right triangles, we can get Fa cosine of 45 for Fax and Fb cosine of 37 for Fbx. In the y direction, Fa sine 45 equals Fay and Fb sine 37 equals Fby. Now we can plug in the values to get the total resultant components in the x and y direction. 52.3 is shown by the red arrow of just adding up all the vectors in the x direction, and 10.2 is shown by the purple arrow by adding up all the vectors in the y direction. The yellow arrow is the resultant force in the direction of the boat that will be heading for those two forces applied. To find the value and direction of the resultant force, as represented by the yellow arrow, we use the Pythagorean theorem and inverse tangent. Plug and chug to get 53.3 newtons as the magnitude of the resultant force and 11 degrees for the direction. In this example, suppose a friend has asked to examine a 10-kilogram box that you were given. Hoping she gets what's inside, and you respond, "Sure, pour the box over to you." She then pulls the box by the attached cord along a smooth surface and is exerted at a 30-degree angle. For part A, we're going to calculate the acceleration of the box. For step 1, draw your free body diagram of the force vectors on the object, represented by the red pinkish arrows. Here are the force vectors redrawn at a point. If you have any vectors at an angle with respect to your coordinate system, you want to draw its components, as seen by the dashed lines for FP. We're going to analyze the sum of the forces in the x direction first, since we're looking to find the acceleration in the x direction. So, sum of the forces in the x direction equals ma. Next, write down all the force vectors in the x direction. In this example, we only have Fpx. Rearrange the equation to solve for acceleration. Fpx can be rewritten as Fp cosine 30 because we know the value of Fp. Plug and chug, and we get 3.46 meters per second squared. Now for question B, we want to know the values of the normal force. So we'll write down the sum of the forces in the y direction, which equals 0, because the box is not floating up in the air, nor is it falling through the floor. Next, write down all the vectors in the y direction. We have a normal force pointing up, Fpy, pointing up, and weight, all pointing down, all equaling 0. Rearrange the equation to solve for the normal force. Rewrite Fpy as Fp sine 30 because we know the value of Fp. Plug and chug to get 78 newtons. The next type of force that we're going to analyze is tension. Tension is applied between two or more objects tied to a rope, string, or chain. We assume that there's no slack in the rope and it doesn't stretch. Here's an example to help us better understand tension. We have two boxes, A and B, which are connected by a lightweight cord and are resting on a smooth, frictionless table. The boxes have a mass of 12 kilograms and 10 kilograms. A horizontal force, Fp, of 40 newtons is applied to the 10 kilogram box. We want to find the acceleration of each box. Step 1. We want to draw our free body diagram of the force vectors on the object. Notice that the tension, Ft, is equal in magnitude but pointing in opposite direction. For part A, we want to find the acceleration of each box. Well, really, we're finding the acceleration of the whole system because both boxes are moving together at the same acceleration. So I went ahead and drew a dashed box around the whole system. For step 1, write the sum of the forces in the x direction equaling ma because we're trying to find the acceleration in the x direction. Write down all the forces in the x direction on the left-hand side of the equation. In this example, we have a positive tension, a negative tension, and a positive Fp, all equaling mass of the whole system, which is ma plus mb, times the acceleration in the x direction. Hey, look at what cancels out. Tension, because they have equal value but in opposite direction. Now, we're just left with Fp equals mb plus ma times ax. Rearrange the equation to solve for acceleration. Plug and chug to get 1.82 meters per second squared. Now, for part B, they would like the value of tension. Well, the last way we just did it, tension canceled out. So to get around that problem, we're only going to analyze part of the system. Now you can either pick the left or right side. I decided to pick the left side because there were less vectors pointing in the x direction. Now we restart with some of the forces in the x direction equaling ma for only the smaller system in the dashed box. The only force vector we have in the x direction is tension. And notice that adding up all the masses in our new system, it's only mb. From there, we can straight plug and chug to solve for the value of tension, which is 21.8 newtons. If you want, you can repeat the process but only with the box on the right side. You should arrive to the same conclusion for the value of tension. Now, in this example, we have two objects around a pulley. This type of setup with two objects around a pulley is also known as an Atwood machine. Here, we have a system of two objects suspended over a pulley by a flexible cable. The mass of the counterweight is mc, which equals 1,000 kilograms, and the mass when carried 4 passengers is me, which equals 1,150 kilograms. For part A, we'll calculate the acceleration of the elevator. Step 1. Draw our force vectors. Two weights pointing down and both tensions pointing up. Now, the trick I tell my students for solving a pulley problem is to straighten out your rope. You may straighten it out in any direction you like. I decided to pick a horizontal direction for the ease of space that I have. However, whichever direction you choose, make sure you redraw the force vectors appropriately, as seen on the figure to the right. Now we can do some of the forces, in my case pointing in the x direction equaling ma. The direction is arbitrary. Just keep in mind that the actual direction on the original display. This particular question is phrased as solving for the acceleration of the elevator. Well, since both objects move at the same rate of acceleration, what we're really solving for is acceleration of the whole system. So all the forces in the x direction is negative meg plus tension minus tension plus mcg, all equaling me plus mc times the acceleration in the x direction. Hey, look what cancels out. That's right, tension. So the equation reduces a bit. Now we can solve for acceleration. Plug and chug. We get negative 0.68 meters per second squared. The negative refers to the system accelerating towards the left. Or, in the original figure, the elevator's acceleration is pointing downward and the counterweight is pointing upward. Now again, to solve for tension, we need to break up the system and only solve for part of it. And again, I picked the left side. The right side would work just as well. So all of my forces in the x direction inside the system is negative MEG plus FT equals ME times AX. Rearrange the equation to solve for tension. I factored out the mass. Plug and chug to get around 10,500 newtons with rounding up. Notice that I plugged in the negative value for acceleration.